Welcome to the fifth part of my little tutorial on the basic modeling techniques in answer set programming. My name is Thorsten Schaub and I will be continuing to use the n-Queens puzzle to illustrate the various techniques to you. In this part, I want to talk about a new experimental feature of our grounder Gringo. To be more precise, we have extended the modeling language, the input language of Gringo, so that we can express finite linear constraint satisfaction problems either by themselves or as a part of a larger encompassing ASP encoding. In this way, we do not need special dedicated CSP solvers in the end, or hybrid systems like our solver Clincon. We can simply use off-the-shelf ASP solvers like Clasp to solve these problems. To get a better idea, let's delve right away in the corresponding encoding of the n-Queens puzzle. There are two things that may strike your eye. First of all, there is a new aggregate, Disjoint, which I will be explaining below. And the other thing is the dollar symbol. Actually, there are lots of dollar symbols here, here, and here. And what they all have in common, they relate to concepts that describe the underlying constraint satisfaction problem. Here, this is a relation, the smaller or equal relationship. Here, actually, we have n different constraint variables, queen 1, queen 2, until queen n, that all range between 1 and n. Here's again a variable. Here we talk about the different constraint variables with queen x, and the grounder actually will replace the x by 1 to n. And here we have operations, addition, and subtraction. Now, before we continue to look at this in detail, let's first contrast it with our previous advanced encoding that shows how these constraints actually are formulated in standard answer set programming. Okay, for this, let's go back to our very basic encoding, since it lists all constraints explicitly. Well, the first thing, of course, to observe is that the position of a queen was here encoded by a binary predicate queen, while here we do this by a variable that has a single argument. You can think of this as a function. So queen 5 maps to a value between 1 and n. So this concerns the generating part. That we put exactly n queens on the board is done with a range variable here, and the fact that we have exactly n such variables. And now we forbid vertical and horizontal attacks. Well, one type of attack is of course implicitly in the encoding here, because each variable will have exactly one value, so say in one row there can be exactly one queen. The other, let's say forbidding queens on the same line that we did here, is done or must be done explicitly via this constraint here. And the two remaining constraints, these guys, actually implement the two integrity constraints forbidding queens on the same diagonal. So this should at least parallel things a little bit. Of course, I cannot delve into details, and actually I would like to encourage you to play with this a little bit. So let's start running this. So let's launch a shell and solve a rather simple n-Queens puzzle, one consisting of 10 queens only, and make it even simpler and ignore these yet unknown constraints with the mysterious name Disjoint. So the only thing we are looking at now is this range restriction here on the 10 variables called queen 1 to queen 10. And this range restriction imposes that they take a value between 1 and n and exactly 1. Okay, let's do that. So here we get the resulting assignment. So the variable queen 1 was assigned the value 9, the same for the variable queen 2, and actually here's even a little difference. The variable queen 10 was assigned the value 10. Okay, so this gives you first of all a feeling how now the answer sets look like, and of course all this can be mixed with standard answer set programming. Now if we remove the comments here, we get actually a reasonable solution, and here for 10 we get this in almost no time. So this is now a solution to the 10 queens problem. Next, let's have a look at the disjoint constraint. After grounding, we obtain here a set of pairs consisting of a term and a value. In term all values sharing the same term are regrouped in sets, and the constraint imposes that all resulting sets must be disjoint. In our example, we only get singleton sets because each term is only attributed once here, for 1 to n, and thus all these three constraints amount to classical all different constraints that one knows from constraint programming. Now let's examine the impact of this in terms of performance as well as in terms of constraints that are induced in the ASP solver. First of all, let's run the best ASP encoding we've come up with so far and launch it on the 300 queens puzzle. And it takes roughly 2 seconds. Here we go, 1.5, 1.6 seconds. And let's compare it with running the constraint encoding. And we get actually a quite similar performance. So we are, let's say, 1 second slower, but that's quite impressive given that we had to spend quite some effort in, let's say, pimping the queens encoding so that we get this performance. And here, with this constraint-based encoding, we get a quite decent performance right away. So that's pretty nice. Let's see a little bit what's happening inside the solver. To do so, we just launch the previous commands with the stats option. This is now the best ASP encoding we have come up with so far, and we see we end up with a ground program consisting of 275,000 atoms, 366,000 rules, and nicely actually in class this is reduced to 90,000 variables and 2,500 constraints. Now let's do the same with our constraint encoding. And before launching this, let me just point out the constraint mix that we achieve here. So we have 5% binary constraints, no ternary constraints, and more than 94% other constraints, which are mainly cardinality constraints, which are treated with dedicated data structures. Now, if we do the same with the constraint encoding, and let me just open up your view a bit by enlarging the window. So we now get 466,000 atoms, which are 200,000 more than we had here, and a little bit more than 100,000 more rules than we got before. Now, however, the problem is not nicely reduced as before, where here, remember, we got 2,500 constraints. Now we are still faced with slightly more than 400,000 constraints, but now the constraint mix is rather different. We have 75% binary constraints and 24% ternary constraints. And nonetheless, we get almost the same performance. Now, what is interesting, actually, you may recall this from a previous part, is we can actually, in the ASP setting, compile away all cardinality constraints with the trans-ext option. So we translate away all cardinality constraints. And as you notice already, this takes quite longer than the 2 previous runs. And in fact, we end up with more than 9 seconds. Even though the resulting constraint mix is similar to the one of the constraint encoding with 75% binary and 25% ternary constraints. However, as you see here, with the constraint encoding, we only got 400,000 constraints in the end, but here we got, wow, more than 1 million constraints. So this then definitely slows things down. So in a nutshell, performance-wise, having a constraint-based approach using integer variables really seems an attractive alternative either to integrate into ASP or even to formulate right away in such a way. In fact, whenever we face a large number of flat constraints, that it be binary, ternary, even longer ones, it is worth checking whether preprocessing techniques from the area of stat solving help us to reduce the number of constraints. So for this, let me just relaunch our constraint problem, or our constraint-based encoding, and count the number of constraints. So we get slightly more than 400,000 constraints. And now I do the same, but kick in SAT preprocessing, which is actually a reduction technique that uses resolution to eliminate variables. And indeed, we were able to reduce the number of constraints. Well, let's say we got rid of more than 50,000 constraints. And the other interesting observation is that we increased the number of binary constraints, but also the number of longer constraints. Because keep in mind, here in this encoding we don't have cardinality constraints or weight constraints, so these are really longer but flat constraints, sort of longer clauses. Okay, but the question now is, does this actually pay off? So we reduced the problem. We also invested time in doing the pre-processing. So this is again the time we measure in our original problem, so 2.3, 2.4 seconds. Now the same with pre-processing. Of course, pre-processing will take some time, but it will reduce the problem. But as we see, we actually get roughly 3 seconds, well, 2.9 seconds. So at the end of the day, it hasn't paid off to reduce the problem. Anyway, such pre-processing is interesting whenever one has such problems where we have a lot of clause-like constraints, and it's always worth checking it. So this was this part of the tutorial. I hope you liked this experimental view into Gringo, and we will be very happy to get any sort of feedback from you, because we want to develop this feature further in the future. Okay, so stay tuned for the next and last part of this tutorial.